Hello, everyone. I'm Sam, or Samuel. I'm studying computer engineering in the College of Engineering, and our advisor slash client, this also served as our senior design project, was Professor David Starbinski, also in the Department of Electrical and Computer Engineering. The title of this project is Misbehavior Detection System for a Cellular Vehicle-to-Everything System. So let's just start real quick with a general problem statement, and then I will get into a quick visual. So to actually understand the effectiveness of this standard, the vehicle-to-everything standard, I'm going to analyze physical layer attacks on nodes in the network. I will just say, with some background, the vehicle-to-everything standard, which I'll talk about more in a second, is a communication standard between autonomous vehicles or semi-autonomous vehicles. So to start this visual, let's say we have two cars. We have this yellow and blue car. Usually, using sensors, they'd be able to detect each other, but let's say this bush is in the way and it's blocking line of sight. They'll collide. But through this basic safety message, that blue car will understand to wait, and that collision will not take place. However, if there's this malicious red car with jamming, it will, with that lack of line of sight and lack of that basic safety message, there will be that collision again. So this project fundamentally is finding ways to differentiate between normal signals and a jammed signal. So there's a lot to see here. This is a general flow chart of how the project went. First, we started out just narrowing the frequency spectrum, getting the actual signal, which is located at 5.9 gigahertz. Once we got that signal form, we put it through a program for some signal processing to get that data, those features. From there, we did some analysis of all that data. There was two types that we focused on, IQ data and resource blocks. Again, I'll talk about those in a moment. And at the end, once we had all of that data processed, we were able to work on getting real-time, this is being jammed, this signal is not being jammed, like notifications. All right, so again, background on the Cellular Vehicle-to-Everything protocol. It is a cellular network protocol using side-link communication, which basically means that there's direct communication rather than, your cell phone will send data to a cell tower and that will bounce around. This is directly between not just autonomous cars and each other, but any other smart vehicle or smartphone. That's the everything part. So smart bikes, just cell phones themselves, anything else in maybe a smart city. But again, yeah, between each other without a cell tower. And as I said, they communicate with these BSMs, basic safety messages, with basic information like GPS location, velocity, and acceleration. And as I said, used for autonomous vehicles. You can see that red box is generally where it's situated. It's around the same area of the bandwidth of the RF spectrum as Wi-Fi, but also, as you can see, some just under where satellites would use to communicate. So let's talk about zoom in a bit, talk about what actually holds the data. So there's these things that the 4G or the LTE system uses called resource blocks, which the V2X standard is based on. It dynamically sends this information, but the bandwidth, instead of just being this one long string of data, it's broken up into these smaller subchannels, and each of these resource blocks, which only take 1 millisecond to send and are randomized. They're different sets that allow for the lack of overlap, the lack of collision, so there isn't just a constant stream of noise on the network where there's a bunch of vehicles in one place. So a quick look at the experimental setup. In the center, you can see kind of our overall setup. There's two desktops. There is, right in the middle lower, is our two signal generators to sync up the radios. On the left and right bottom corners, you can see our actual radios. And peeking out in the top left is the oscilloscope to actually confirm signals are synced and working correctly. So the product itself was really split into three sections: the hardware, which was setting up the radios and actually creating a jammer, then getting that data and processing it, extracting it, and then finally creating a machine learning algorithm to thoroughly actually detect that jamming or lack of. So to start with the hardware portion, we started just by syncing the radios with a signal generator. They needed a way to basically have a timestamp and understand where each of them were. And we started my group early in the fall with basic ping tests. So just, here's some random information. Can you receive this? Yes. And then it sends a response back. Yes, I can understand your information. Then we found an open source library to actually generate the vehicle to everything signal. And that is the middle animation. And then the jammer code, which you see on the left, that was an earlier prototype. It's now been shifted slightly. But as we iterated, we got this overlaid signal on the right, which combines both the jammer and the actual code. I'll say quickly, the top is called a waterfall diagram. It's a brief way to visualize the RF spectrum. And then the bottom is just a plot with IQ data, stands for interphase and quadrature, but all you really need to know is it's a slice being like of a waveform that's being received, and another way to just visualize a radio signal. So then with the data, we were able to identify by reverse engineering this big code base in the programming library, get all that data, all the resource block and IQ data, extract it, get timestamps, and also the actual values. On the right, you can see that is the IQ data. It's basically a location on a complex graph, as well as resource blocks, which are not shown here. And then finally, we formatted it for use in a nice CSV type file, just for use by the machine learning team so they could feed it into their Python scripts. Finally, for the machine learning portion, we used a prototype convolutional neural net for testing the jammed resource block groups. We first worked on between IQ and resource blocks, but we ended up deciding on looking at these resource blocks. And as you can see on the right, this is different types of resource block pools, and multiple epochs, multiple test runs to get it to learn when a signal is jammed. So the overall results, through these machine learning models, we were able to detect jamming with an accuracy of about 81%. This really does two things. It allows the vehicles themselves to be able to communicate, go from that leftmost picture where they're being jammed to intelligently move to another wavelength and continue to communicate despite that jammer. Additionally, this research and this protocol is still in its early stages. It's only a couple years old, so this will help us to build and actually get this properly implemented in autonomous vehicles, many of which are still in prototypes. So it's not only an important milestone, but it's also just a very interesting find. One thing I just want to say before I finish is acknowledgements. This is my team. There was 6 of us. Without them, this project was really put on all our shoulders equally, and I'm very thankful I had them. And then also our PhD student advisor, Stefan. So yeah, I'm very thankful to have all of them, and it was really an amazing experience. Yeah, that's all. Questions?
Do you think there could ever be like a battle between the jammers getting more sophisticated and your algorithm for detecting the jammers ever getting more sophisticated in the future?
Yeah, absolutely. When it comes to any type of security or like denial of service, there's always kind of a race between those malicious users and then the people actually making the standards. So the creators of this protocol will find another way to make things jump around. The attackers will find a way to kind of figure out what it's going to randomly jump to next, and then they'll just keep adding layers of obfuscation, but that's just how it works.
So for your results, you showed that you could achieve an accuracy of 81%, which is, I think that's pretty impressive. But I'm wondering, for actual use in a vehicle, I wonder what would it take to bring that 81%, into the 95 range or something? Do you have some idea of the next steps that would be required to get it that much further?
I think just as we get more specialized hardware, that's really the key thing. Our project was more, how should I say, it was using more generic hardware, so we didn't have that specialized hardware, like firmware, et cetera, to perfectly accurately detect, and sometimes there is a little bit of extra signal noise. But when you have these narrowband chips that look specifically at that wavelength and only in like very specific segments of that wavelength, like I talked about with the resource blocks, then the accuracy should go up naturally.
Can I ask you a question back to the question of jammers? So first of all, we could have totally used this technology yesterday when my daughter, for the first time as a new driver in the CAS parking lot, had precisely the scenario of your first image of a blind turn and scraped the entire side of our car against the CAS concrete wall. But the difference was there was no jammer, right? That happened anyway. We also don't have very sophisticated cars. So I'm wondering who the jammers is. There's assumed people who are jamming in the empirical version of this, the real world scenario. Where do we understand where these jammers are located and why they're jamming such a thing as communication between and among cars?
So, yeah, like this example is still more of a theory because autonomous cars at best can do basic like navigation through a parking lot, but later on there will be these malicious drivers just driving along and they basically just blast on all frequencies, try to cause chaos. There's no real specific like use case for or reason for these jammers. They usually just like to cause chaos. But yeah, so as the protocol evolves, there will be more precision with the autonomous cars themselves, and then more reason for attackers who want to just cause chaos.
Thank you very much.